Hello, my name is Daniel Benvenuto. I'm in Professor Delacorte's Physics 106, Section 1, and today I will be talking about Van de Graaff generators. To start off, what is a Van de Graaff? It is a device used to generate high electrostatic potentials through means of the Triboelectric effect that takes place within its hollow column. This generator creates high voltages at low current levels. A moving belt within the column accumulates the electric charge and carries it up to the hollow metal globe on top. So before we get more into exactly how this works and how it creates high electrostatic potential, I'd just like to talk about the history of the Van de Graaff first so that we understand that a little. It all started with a man named Robert J. Van de Graaff. Born in 1901, he was a renowned American physicist, and while working as a professor at Princeton University, he developed the first model of a Van de Graaff in 1929 by using a tin can, a small motor, and a silk ribbon. So he continued working on the model, and in the following years he perfected it using funds from the Princeton Physics Department. It was capable of generating 1.5 million volts of charge. He continued working to try to perfect the model even further, and in 1933 Robert constructed a 40-foot tall Van de Graaff capable of generating 5 million volts of charge. These huge devices had to be moved indoors to finish their construction after an accident with a few pigeons occurred. These devices are now an exhibit at the Boston Museum of Science, where visitors can go and see how they work. So a few physics concepts behind the Van de Graaff. The Triboelectric effect. This controls everything that happens within the Van de Graaff. It is a type of contact electrification where certain materials become either positively or negatively charged. This change in charge of the material occurs because of the transfer of electrons between the two materials. A common example of this effect is a glass rod being rubbed with a silk cloth. So we see here to the left, we have a glass rod which normally has a net positive charge, and a silk cloth which normally has a net negative charge. So when rubbed together, electrons will be rubbed off the glass rod and passed to the silk cloth, leaving a net positive charge. So how do we determine what will have the positive and what will have the negative charge? This chart, called the Triboelectric table, exists to help determine how the two materials will react when put into contact based off of how likely they are to go net positive or net negative. So as we see here, glass is higher in the chart than silk, and we have silk down here. So that explains the net positive charge on the glass rod when rubbed together. So you can get any two materials on this chart, and the one that's higher up, more positive, will retain the net positive charge, and the one that's lower will have the negative charge upon contact and friction. So let's take a look inside the Van de Graaff. In the Van de Graaff, the triboelectric effect takes place within the hollow column, where a belt, made usually of insulating rubber, is attached to an upper and a lower roller, which are made of two different materials. They rapidly spin near an upper and a lower comb made of conductive material that holds positive charge. So you see here to the left, you have your lower roller. Down here you have your upper roller, both made of different materials, as I said earlier, and your lower comb and your upper comb. And this belt will spin rapidly around, rubbing against the upper and lower roller and also the combs. And depending on the materials that they are made of, certain charges will be accumulated in certain areas and carried up the belt. So as you see here on the right, we have an image of a roller here, and the roller is made of a material that holds a net positive charge, whereas the rubber is made of material that holds a net negative charge. So when rubbed, an accumulation of positive charge is created here, while all the electrons are carried up on the belt. So that's just a close-up look at one of the rollers. But let's see exactly how a Van de Graaff generator might work using this physics concept here. So a motor belt turns a motor turns the belt, causing it to rub against the two rollers near the combs. A negative charge accumulates on the inside of the rubber belt, while a positive accumulates on the outside. Positive charge accumulates on the glass acrylic upper roller, a potential material that could be used to make that roller, while negative charge accumulates on the lower roller, made of a material different from the upper roller, perhaps a metal of some sort. A net positive charge comes from the positively charged conductive lower comb, having its electrons repelled by the nearby negative lower roller, then these protons being attracted towards the roller and carried upwards by the belt and towards the upper comb. So let's pause right here and let's just explain a little bit. So we have our lower roller here and our upper roller up here, and there is a net negative charge being accumulated down here, whereas there's a net positive charge being accumulated up here. And what's happening is, as the belt is rubbing against this roller and accumulating this negative charge, this conductive comb right here, which had positive and negative charges, is having all of its negative charges repelled because it is right here next to the lower roller, which has an accumulation of negative charge, and it's starting to accumulate a very large positive charge here and on the comb because of the repelling of electrons, and these positive charges are attracted to the lower roller because it has a net negative charge. And what happens is, as they travel up to meet with these electrons, they are caught by the belt and taken up towards the upper roller because the belt is separating the lower roller and that lower comb. So then, as these positive charges are coming here to the top, what's happening is this upper roller, made of a different material, is retaining a net positive charge as it rubs against the rubber belt. And these positive charges are attracting all of the electrons from the comb and leaving a net positive charge on this comb. And all these protons going up are being repelled because of this upper roller net positive charge. And all the protons that are accumulating on the upper comb are also being repelled outwards towards the outskirts of the inside of the hollow metal sphere. Let's move down here. So this strong electric field surrounding the upper roller induces a high electric field near the upper comb, causing its electrons to be stripped and creating a net positive charge on the upper comb, as I said earlier and showed. And then what happens is these excess free protons from the upper comb are taken by the metal sphere and are dispersed and gathered around the outer shell. So not only do they stay within the outside, they're actually dispersed and they go along the outside of the metal sphere after they are repelled off the comb due to the accumulation of positive charge from the upper roller having its effect on this metal comb. The great constant accumulation of positive charge on the outer shell develops a huge electric potential. When this potential becomes too great, the protons react with air molecules ionizing the air, and charge is leaked in what we see as arcs. These small lightning strikes here that I depicted. Charge leakage can also occur when a neutral and net negative object comes near the charged Van de Graaff. So pretty much what that paragraph is talking about is sometimes we see little electric kind of shocks coming from things that have a very built up electrostatic potential. The reason we see that is because charge is trying to leak through and pass on to its opposite attraction, whether that be a negative or a positive charge. And sometimes when the potential is so great, that charge will leak through the air to get to where it needs to go, and we will see that in these arcs. So this can occur really in a lot of situations. It can occur between Van de Graaffs, as we see here. It can just occur in the air with materials surrounding the Van de Graaff. It can occur with an object that perhaps is charged oppositely from the Van de Graaff, such as like a net negative charge here, or it can even occur with our hand, which is neutrally charged when it comes near a Van de Graaff. As we saw several times with Professor Delacorte, sometimes we may receive a shock. So let's talk about the use of the Van de Graaff nowadays. Well, back then, the Van de Graaff was actually used as one of the first particle accelerators. Particle accelerator is a machine that uses electromagnetic fields to propel charged particles at very high speeds and energies while containing them in defined beams. Although the Van de Graaff is no longer used as an accelerator, it set the stage for newer technology and pioneered the research of particle physics, which is a very extensive field nowadays. And the other most important use of the Van de Graaff is for simply education. We learned so many physics concepts from these machines. We learned about the basics of charged particles. We learned about electrostatic attraction and repulsion of charges. We learned about electric fields, transfer of charge, and we can get a real nice shock from these things too. That is all you need to know about Van de Graaffs. Thank you so much for watching, and have a great day.